Hi, it's Mr. Anderson, and this is AP Physics Essentials video 34. It's on the magnetic domains. In this picture right here, my daughter and I are both playing with ferrofluids, which are tiny little liquid magnets that can respond to a magnetic field. And so in this video, what I'm doing is I'm taking a magnet, holding it underneath the ferrofluid, and you can start to kind of visualize these magnetic fields. I can then turn it sideways, and you can even see the north and the south pole. And so these tiny little ferrofluids are made up of these 100 angstrom little magnetic domains, which are tiny magnets within the magnet itself. And so if you have ferromagnetic material in the form of a magnet, what you're going to get is a north pole and a south pole. Again, you'll never have just a north pole by itself or a south pole by itself, but if we were to look inside that ferromagnetic material, we would find that there are these magnetic domains, which you can think of as tiny little magnets, and each of those tiny magnets have their own tiny little fields. And so if you break a magnet in half, have you broken it? No, you've just created two magnets. And you could keep breaking it in half over and over and over until you get to the level of these tiny magnetic domains. And if these line up, if they align, then we've got an overall magnetic, ferromagnetic material. And they can do this by putting them inside an external field, or sometimes it'll just spontaneously or naturally occur. And so if we have a bar magnet, it's got a clear north and a south, we can make sure that it's magnetized by holding a compass up on either side. And you'll find that the south end of the needle points to the north end of the magnet and vice versa down here. Now if we break it in half, that bar magnet in half, what have we done? Well, let's use our compasses again. If we put them on either side, what you'll find is that we've now created a south pole at this side, and then we've created a north pole up here. So we could do this again and again and again, and we just keep making smaller and smaller magnets. So there must be magnets within the magnets that are causing that magnetism. And so you can think of it like this. In a block of iron, we've got all of these domains, which are going to be tiny magnets inside it. But if the whole thing isn't magnetized, they're going to be pointing in every which direction, and they're going to be separated by these domain walls. And so if you take something that's not magnetized and you magnetize it, what you're really doing is you're lining up all those magnetic domains. If they're all pointed in the same direction, then you've magnetized that overall object. So let's say I want to go back again. Well, let's say I want to go from an object that doesn't have a charge to one that does. Well, this occurs in nature. Lodestone, scientists and humans have known this for hundreds of years, are naturally magnetized pieces of magnetite. And so how does that work? Well, there's speculation that it could be that they're being formed, since we mostly find them on the surface of the earth, near a lightning strike. But what it's doing is it's lining up these domains. If you want to do this in the laboratory, what you do is you take a chunk of some ferromagnetic material, like iron, for example, and we put it inside an electric field. So we're going to put it inside a magnet. And you can see at this point that we've got all these domains. Again, they're much smaller than this, but we have all these domains, and they're pointing in every which direction. But if we can apply a magnetic field to it, watch carefully right here what happens if we let it sit there for a while, is that we're going to start to eliminate a lot of those domain walls. We're going to start to eliminate a lot of those domains. And so overall, this now is going to have a magnetic field. It's going to be a magnet. It may last for a certain amount of time before eventually those domains go back to where they were before. And so do you understand how these magnetic domains lead qualitatively to the overall behavior of the magnet? I hope so, and I hope that was helpful.
We've all heard of magnets. Magnets are what make your car run. They're what generate the electricity that lets you read a book at night. And they're what let you pay for your gas with a credit card. But what exactly is a magnet? What makes some materials, like iron and neodymium, magnetic, while other materials, like copper, tin, and plastic, are not? To answer that question, we'll have to look through a microscope. Scientists now believe that all magnetic fields are created by those all too familiar charges from your days of chemistry: electrons. All moving electrons, whether they're zipping down a power cord or orbiting around an atomic nucleus, generate a tiny magnetic field. Those fields may be small, but they add up, with the potential to create fields large enough to encompass the entire Earth. When we look at this piece of iron under a microscope, we see what appear to be tiny cells. These cells are called domains. In metals like iron, quantum mechanical effects cause the electrons in these domains to share the direction of their magnetic field with other electrons. As a result, each domain has an individual magnetic field. In a non-magnetic material, these fields point in random directions, like toothpicks scattered on a table. The thousands of domains pointing one way cancel out thousands pointing the other. The result is a non-magnetic piece of iron. When we look at this magnet, however, we see that the domains are preferentially aligned in one direction. What has happened is that as this magnet was made, its domains were twisted by an outside force, such as another magnetic field, so that most of them point in the same direction. Instead of canceling out, all these magnetic fields add up, creating a much stronger magnetic field that surrounds the entire piece of iron. And we get a magnet.